So conics and quadrics are basically zero set of degree 2 polynomials. Conics are zero set of degree 2 polynomials in R2, so they are curves, and quadrics are surfaces. Yeah, so zero set of degree 2 polynomials in R3. Yeah, so degree 2 is missing here. Degree 2. Okay, so somehow this display is vanishing. If I can change this display. No, this is not what I wanted. 1 second. Let me set this up and then we'll do it. Oh. Yeah, let's see if it works. It doesn't. Okay, let's not worry about it. Okay, so this is so this is yeah, so as I said, conics are zero set of degree 2 polynomials in R2. So for instance, circle, parabola, hyperbola. So our general degree 2 polynomial looks like this, yeah. It will, so for instance, I mean, if you, so I've written two A11, where A11, A12, A22, B1, B2, and C belongs to real numbers, yeah. So x, for instance, x1 square plus x2 square equals 1 is circle, right? So we know that hello, are you there?
Yes, sir.
Okay. So so there are some degenerate conic and there are some non-degenerate conics. Yeah. So for instance, non-degenerate conics will look like circle, hyperbola, parabola, but there are some degenerate conics, meaning and they don't look. I mean, this is what you expect typically, but but some of them are not nice. Yeah, degenerate conic. So for example, you consider the equation x1 square plus x2 square plus 1 equals 0. Yeah. So what is the zero set of this thing? What will be the zero set for this equation? So what are the point? So basically, you are looking at the graph, yeah, graph of this. So what will be the graph of this equation in R2? Yeah, can you say it louder?
So is it +1 or -1?
+1. So the graph will be? Come on, guys.
So I think it's complex.
Right? There can't be any point. Yeah, so it's empty set. How about this one? X1 square plus x2 square equals 0. Forget about the +1. Then what will be the graph?
The origin. So we're not able to see a screen.
Yeah?
Origin.
Origin. Yeah, so there is only 1 point. So 1 point. Yeah. So so in this case, it will just be origin. Yeah. So depending upon, I mean, if I so you can get 1 point, you can get empty set. Of course, so you can also consider this line. X1 square equals this conic x1 square equals 1. Yeah, or x1 square plus -1. Yeah. So what is this? This corresponds to 0 set. It's 2 lines. Yeah. So it is x1 equals 1 or x1 equals -1. Right. So you get 2 lines, for instance. So you can get 2 lines, and so these are all degenerate conic, meaning this is not what you expect normally, right? So normally you would expect things to be somewhat more like circle, hyperbola, parabola, but these are some weird cases. And then there is you can also get 1 line. Can you tell me an equation of, so that is, this is 2 lines, yeah? X1 equals 1 and x1 equals -1. So there are 2 lines. Can you give me a situation where you can get 1 line? Say it louder.
X1 square equals 0.
X1 square equals 0. Yeah. So for instance, this one will give you the y-axis or x2 axis, so to speak. Yeah. So 1 line. Yeah, so there are many possibilities of degenerate conic, and non-degenerate conics are circle, parabola, hyperbola.
The circle would also include the ellipse.
Circle meaning ellipse, yeah, that's right. So ellipse, parabola and hyperbola. Circle is a particular kind of ellipse. So maybe I should just write ellipse, yeah. Right. So what we will see, we will study we'll try to classify. So given this degree 2 equation, which we denote by fx1 next to, when will it be a non-degenerate conic? When it is a non-degenerate conic, which one is it? Is it a hyperbola, parabola, etc.? One can decide it based on these coefficients. So note here I have put 2A12 because we'll do some matrix operations and then this 2 comes out naturally. Of course, I could have just written A12, but even if I write 2A12, it doesn't change anything, right? Because you can take half of that original coefficient, yeah? So basically this equation, one can write it in terms of matrices like this, yeah? So you consider the matrix Aij's, A11, A12, A21, A22, but you make sure A21 is same as A12, yeah? And then consider X1, so the vector X1, X2, X1, X2. These are the coordinates on R2, yeah? So this equation, A11 X1 square plus 2A12 X1 X2 plus A22 X2 square is these three terms come from this multiplication, yeah. And then B1 X1 plus B2 X2, you can get it by this multiplication. And then C is some constant, yeah, some real number. So you can write Fx1 X2 in this form, where Aij is a symmetric matrix. Symmetric matrix. Yeah. So because A12 is A21, yeah, and B12 is some column vector. Yeah, B1, B2. So the B is some row vector. Yeah. So if you you can write Fx1 X2 by as this. Yeah. So if we so now the point is we know that if we are given a symmetric matrix, then by spectral theorem we can diagonalize it. Yeah, in fact we can diagonalize it using an orthogonal matrix. So orthogonal matrix means that the angles also don't change. Yeah, so we are basically by choosing new coordinate coordinate axis, we can make sure that A is we can transform A into a diagonal matrix. So anyway, so we will show that every non-degenerate conic is one of these things, and the proof is by first using the spectral theorem, we can make sure that there is a orthogonal matrix P such that P transpose AP is diagonal, yeah, since A is symmetric. So in fact, we proved it more generally for any complex matrix as long as it's Hermitian, in fact, normal. So here we are using the fact that A is Hermitian, yeah, but also real. So real Hermitian means it's symmetric. So and we can find an orthogonal matrix P such that P, but we are saying that P is not unitary but orthogonal. Yeah, so we are applying the situation where we are looking at real matrices, not yeah. So the linear transformation is between Euclidean spaces and not Hermitian spaces. Yeah, so A is a map on A is a linear transformation on a Euclidean space. Okay. So so now what you can do is you can change these coordinates. Yeah. So zero set of this F is given by X1, X2. If I apply P transpose to it and get this X prime, yeah, then the shape of that so the shape of the zero set will not change. Yeah, we are just changing the axis. If I apply P transpose, the shape remains same. It's just that instead of X1 and X2 axis, I'll get some other pair of orthogonal lines. Yeah. So if I think in terms of I think of the solution in terms of these x primes, then the shape doesn't change. So so we are allowed. So this transformation doesn't change the shape. Yeah. But the equation in terms of x prime will change, and it will become simpler. Yeah. So if you put x prime as p transpose x tilde and b prime as bp and a prime is this, then look at what happens to this equation. Yeah, so yeah, I've written it upside down, but it doesn't matter. So then x prime transpose a prime x prime plus b prime x prime plus c is same as, now you substitute for x prime transpose as p x tilde. Yeah, then then it becomes x prime transpose p transpose a p x prime plus yeah, so there's maybe, and this also I can do it in 2 steps. So x prime is b prime is b p and x prime is p transpose still, yeah. And what is p transpose? P transpose is identity, right? Because p is an orthogonal matrix. So this becomes bx, and what does this become? So again, x prime transpose, you have to substitute p transpose. So this will become identity. Sorry, this will become identity. This will become identity. So you'll get x transpose ax bx plus c, which is same as fx1 x2. Yeah. So what we get is fx1 x2 is 0. So this 0 set fx1 x2 equals 0 if and only if this is 0. Yeah, in the new coordinates. So the 0 set of fx1 x2, the conic defined, or rather the conic defined by fx1 x2 is looks same as the conic defined by this new equation. Yeah. And this new, yeah, so I said, so b prime will be some column vector, some row vector, b1 prime. Yeah, so maybe I should just write this down. So let's call this b1 prime. It will be some row vector b1 prime, b2 prime, and a prime is a diagonal matrix. Yeah, so it's a11 prime, a22 prime, and then 0 0. Yeah, so this is how it looks like. So if you try to analyze this equation, and this one, this left hand side, then this is same as saying that a11 prime x1 prime square plus a22 prime x2 prime square plus b1 prime x1 prime plus b2 prime x2 prime plus c is 0. Yeah. Plus c 0. Yeah, we haven't, c doesn't change at all. Yeah. So this is so the conic defined by f and conic defined by this are same, more or less same. Yeah, they look same. It's just that maybe different coordinate axis you'll have to. Now what we'll do is we'll do some sort of translation. Yeah. So suppose a11 prime and a22 prime are non-zero. Yeah. Then what we can do is we can try to complete the square. We don't want too many terms. We want to minimize the number of terms so that it's easier to. So if a11 prime is non-zero, then we can write it as x1 prime minus some number whole square to absorb this term. Yeah, this is how we solve quadratic equation. Right? So that number is this. So I mean, I'm doing some sort of translation by this point, and similarly for B2 we'll have to do a similar, for 2s we'll have to do a B2 prime and A22 prime. We'll have to do a similar translation. So these two terms will get absorbed, b1 prime x1 prime and b2 prime x2 prime, but the constant c will change. Yeah. So this equation, let's give it a name, double star. double star becomes this if we do this change of variable, but instead of writing x1 double prime, I'm going back to x1. Yeah, the shape doesn't change. Yeah, so instead we'll have too many primes and so on. Right, becomes this by replacing x1 double prime, or rather x1 xi double prime by xi. Yeah. So this is what we do. Then it becomes a11 prime times x1 whole square plus a22 prime times x2 whole square plus c prime equals 0. Yeah. So this works if a11 prime is non-zero and a22 prime is non-zero. Yeah. So in this situation, we have the shape of this equation and the shape of this equation are going to be same. Yeah. So we are talking about the same conic. Just that either it's rotated and it may be rotated and translated. That's all. Yeah. Now, we know that this is a conic, right? So this is a fx1 x2 is a degree 2 equation. So degree 2 equation means that not all of these should be 0. Yeah. So a11, a12, a22, they can't all be 0. Yeah. So in particular, it tells you that the matrix A is non-zero. Yeah. So since f is a conic, fx1 x2, maybe that is what I should have written. Fx1 is x2. Since fx1 x2 is a conic, A must be a non-zero, and if A is non-zero, its conjugate is also non-zero. So A prime is non-zero. So this vector, if I think of it as this vector, A22 prime, this is a non-zero vector. Yeah, it's not, both of them can't simultaneously be zero. Yeah. So now I mean this. So remember, up to this equation, we are not really using the fact that a11 and a22 are 0. Yeah, only when we are trying to get to this equation, we are saying that they should be non-zero. Yeah. So now, if c prime is 0, c prime, yeah. So if c prime is 0, we know that this gives you a degenerate conic. Yeah. So we'll have to assume that C prime is non-zero. So there are many cases, yeah. So if C prime is non-zero, then by dividing by C prime, we may assume C prime is 1, yeah. So you can divide this whole equation by C prime, and you can assume that C prime is 1. Now you look at these A11 prime and A22 prime. So if both are negative, then that tells you that there is no solution. Yeah. If both are positive, then it tells you that this is a ellipse, right? Am I doing it right? No, I've reversed it. Sorry. So if both are negative, then it is an ellipse. Yeah. No solution. And if one is positive and one is negative, then it's a hyperbola. Yeah. So let's try to so if you look at So if you look at your matrix, yeah, symmetric matrix, you can just look at its eigenvalues. Yeah. So this A11 prime and A22 prime, they just tell you what the eigenvalues are. So if both the eigenvalues have different sign, they are both of them are non-zero and they have different sign, then you can conclude that it's a hyperbola, right? From these conclusions, there are different sign and see and the constant, then it's either hyperbola or two line. It may happen that C prime is zero, yeah. So if both of them have different sign and then it's either hyperbola or a pair of lines, and whether if you know that it's non-degenerate, then it must be a hyperbola. If both have same sign, so both are positive or both are negative, and you know that the solution set is non-empty, then it must be ellipse. Yeah. So if you know that the conic is non-degenerate, then by just looking at whether the matrix is positive definite or not, you can whether the matrix is non-degenerate positive definite, then it is an ellipse, and if it is non-degenerate but not positive definite, then it must be hyperbola. Is that okay?
Sir, I'm confused why when both the coefficients are negative, then it's an ellipse.
If both A11 prime and A22 prime are negative, then what you get? Then you'll get that A1. Then you get something like minus of A11 x1 square minus of A22 x2 square equals 1. Yeah. So these two are positive, so this defines an ellipse.
Okay.
Right. So you are in this case. Okay. If both A11 and these are both positive, then of course left hand side is always positive. Yeah. Left hand side of this equation is always positive, and you get empty set. Yeah. No matter what x1, x2 you put. Is that okay?
Yes, yes.
And if one is positive and the other is negative, then you get a hyperbola. That also is clear, right? Yeah. Okay, and now the situation is that, so we know that both of them, both A11 prime and A22 prime can't be zero. Yeah. Yeah. At this stage itself, we can say this. Yeah. So since A is non-zero, implies A prime is non-zero, implies this condition. Yeah. A11 prime, A22 prime is non-zero. Okay, so we can assume so one of them must be non-zero. So so let's say let's assume the other one is zero. So if one of the eigenvalues is zero, then you get a parabola. So what happens is you can complete the square for one which is non-zero. Suppose if this let's say this happens, yeah. So this case, then you can transform the equation to A11 prime times.
Sir,
Yeah. Parabola or, yeah, tell me. Yeah, tell me. Hello, are you there?
sir, your voice was breaking. It's about.
Okay. Is it better now?
Yes, sir.
Oh, okay. Any questions?
We didn't hear what you just said, sir. I mean, before 1 minute.
Sure. So now is the case where one of these A11 prime or A22 prime is zero. Yeah.
Sir,
So let's just assume A22 prime is 0 and A11 prime, and hence A11 prime is non-zero. Yeah. This case means that A11 prime is non-zero. Yeah. So in this case, what happens is that A11 prime, so the equation becomes, so again, by the same trick, you can absorb this linear term for x1 prime. Yeah. So it will become A11 prime x1 square plus some B2 prime x2 plus c prime. Yeah. This is how the equation will look like. Yeah. And in fact, you can by changing x2 prime by a linear function, you can absorb the c prime as well. Yeah. So you can if b2 prime is non-zero. Yeah, so okay, so let's leave it. So let's not worry about it. Anyway, it will not change anything. Which case did you not understand? So ellipse solution and hyperbola, did you understand?
So we weren't able to hear you for a bit. Your voice was breaking. So, like after Hridya asked the question and you explained the ellipse again, after that you weren't able to hear you.
Yeah, so after ellipse, I mean, if both of them are positive, then of course there is no solution. Yeah. And if one is positive and one is negative, then it's a hyperbola. Right? Because it becomes like x1 square minus x2 square equals 1. Yeah. So it is a hyperbola. So with some coefficient in front, but that will only change the shape of the hyperbola. So these are the three cases. Yeah. Are these three cases okay now? Do you understand?
yes.
Yeah.
Yeah.
Okay. Now we are dealing with the case when one of them could be 0. One of A11 prime or A22 prime is 0. So exactly one can be 0. Both can't be 0. So let's assume A22 prime is 0 and A11 prime is non-zero. Yeah. The other case is similar. So in that case, the equation becomes this thing. Yeah. Is that okay?
Yes.
Yeah. Now in this case, what happens is this is so if so now there are cases again. So if parabola or it could be uh, degenerate conic. So yeah, so in this case, so what happens is if B2 is B2 prime is 0, then this is a degenerate conic, right? Then degenerate. Yeah.
Why isn't there x1 terms in the above equation?
Say that again.
Why isn't there an x1 term?
Because we can absorb the x1. A11 prime is non-zero. Yeah. So we can have we can do this transformation again. Yeah. So the x1 term will be absorbed, but x2 term you can't absorb. Yeah. So there will be a linear term in it. So if B2 prime is 0, then degenerate conic. Yeah. So basically either a pair of line or one or just one line. Both of them are positive or maybe empty set. Yeah. Depending upon. So if C prime is positive and A11 prime is positive, then empty set. If they have opposite signs, then pair of lines. And if C prime is 0, then one line. Yeah. So it's either then it's a degenerate conic. If B2 prime is non-zero, then of course you can absorb this C as well in B2 prime, yeah, by change of coordinates, or you know that this looks like a parabola. Yeah, so then parabola. So you change, I mean, you have to do the translation by x of x2. So, and you can see that it's a parabola. It's a translation of a standard parabola. Is that okay?
Yes, sir.
Yeah. So these are the various cases you get so if you are given an equation, then you can look at the eigenvalues, and that will tell you. So in some situations, it will tell you exactly where it will. So if you also know that it's non-degenerate conic, then you can more or less from eigenvalues itself you can decide whether it's a parabola or a high. So if one of the eigenvalues is 0, then it must be a parabola. If both the eigenvalues are non-zero, then it is either ellipse or hyperbola, depending upon whether they have opposite signs or they have the same sign. Yeah. But you'll have to rule out the degenerate conic. So of course, it may be a degenerate conic, but as long as it's non-degenerate, just by looking at eigenvalues, you can decide. So maybe let me jot down this observation. Yeah. Let fx1, x2 equals 0 be a non-degenerate conic, and f be given by. So let's write it x transpose ax plus bx plus c. So any f you can write it this way, where A is 2 by 2 symmetric matrix. Then the conic is a parabola. So there are three cases. Yeah, is a parabola if one of the eigenvalues, or maybe let's say determinant is 0. Is 0. This tells you that it has to be one of the eigenvalues must be 0. Yeah. Or E is singular is one way we could have said. Ellipse, if A is positive or negative definite, A is positive definite or negative definite. Or maybe I'll write it this way, plus or minus A, if A or minus A is positive.
So then we can say the determinant is positive, right?
Say that again.
Can we generally say the determinant A is positive in these two cases? I mean, can.
Yeah, we can also say it this way. Yeah, so just by looking at the sign of the determinant, yeah, that is even better. Determinant A is positive.
So, but suppose both of them are negative, and both of them are positive. A1 and A2 are positive, then it has no solution. It's not an ellipse, right?
Yeah, so that's why I'm assuming it's a non-degenerate conic.
Oh, okay, non-degenerate.
Yeah, so if you know it's non-degenerate, then you can decide it. If it is a degenerate conic, then you don't, I mean, if you don't assume that, then maybe it's a degenerate conic. Yeah? So it's either a degenerate conic or this. Yeah. So in all these cases, hyperbola if determinant. Yeah. So this is even better. Yeah. Negative. So just by looking at the determinant of A, you can decide whether it's a parabola, ellipse, or hyperbola. So in all these three cases, it's also possible that it could be degenerate cone. Yeah. But if it is not degenerate, then it must be, I mean, the determinant of the matrix determines it. Yeah. So this is about conic. And now let's, so you can do a similar analysis for 3x3 matrices, yeah? So, there are many many degenerate cases. So we'll assume to start with, we'll only look for non-degenerate guys rather than looking at all possible cases, yeah? So I don't want to look at all possible. I only want to look at non-degenerate cases. I mean, there are many degenerate cases, empty set, it could be line, it could be pair of lines, and now it could be a plane, it could be pair of planes, and so on. So there are many cases, so I don't want to look at all that. So I would just want to look at quadrics, yeah? Non-degenerate quadrics. So we can start by the same philosophy, yeah? So any quadric, so quadric is given by zero set of degree two equation in R3. Yeah, so there will be three variables involved: x1, x2, x3. Yeah, and again, since it's degree 3, so the coefficient of x1, x2, again we can divide it by 2. Yeah, x1, x2, and x2, x1. And write it in terms of matrices. So you can write it as x1, x2, x3, a matrix A, a 3x3 matrix A, and x1, x2, x3, plus some row matrix B times x1, x2, x3, plus some constant C. Yeah. So A is symmetric any, so maybe any degree 2 polynomial fx1, x2, x3. You can write it this way. So the degree is 2, then you can write it as this, where A is polynomial with real coefficients. Yeah, so it's the real number is important with coefficients in R. So not arbitrary field, where A is symmetric and symmetric matrix, and B is row vector. Yeah, so it will be B1, B2, B3. Okay. So this is like the previous one, and then you can ask when is it? So you can ask what are the various cases you can get. Yeah. So again, by spectral theorem, there exists P orthogonal such that P transpose AP is diagonal. Yeah. So again, we will do this transformation. So our x prime tilde will be just P transpose. P transpose is P inverse basically. Yeah. P inverse x. Yeah, like we did in the above case. And then this fx1, x2, x3 is 0 if and only if this x prime transpose, let's call this let's call this delta now instead of A prime. Yeah. Diagonal matrix D delta X prime plus this is yeah, so BP so X tilde is PX prime, yeah. So B prime was so I think this is okay. So it will be some other B prime. So let's just write B prime, yeah, for some other column. B prime X prime. So B prime is just BP, yeah, like in the previous case, plus C equals 0. Yeah, so these two are gives you the same equation. Okay, so again, so this equation, if you think about it, it becomes A11 times X1 square plus A22. So we'll ignore all the primes, yeah. So the zero locus of this and zero locus of what I'm writing has the same shape, and I'll just ignore all the primes so that we don't have to worry about writing primes. Yeah. A33 x3 square plus b1 x1 plus b2 x2 plus b3 x3 plus c equals 0. Yeah. So enough to analyze this equation. Yeah. Now again, if some of these AII is non-zero, then you can absorb things. Yeah. And absorb the corresponding linear terms. But maybe so we'll have to deal with various cases. Yeah. So let's say consider the case one. AII is not equal to 0 for all I. Yeah. Yeah. So for all the AIs are non-zero, then you can observe all the three, and what you get is then star can be transformed to the following by change of coordinates, rather by change of origin. Yeah, by translation. So what you just do translation, and it becomes A11 x1 square plus A22 x2 square plus A33 x3 squares equals C. Yeah. And so if C happens to be 0, then it will be something degenerate. Yeah. So let's just assume C is non-zero, and hence we can divide by C and make sure that it's 1. Okay. So equals 1 if the quadric is non-degenerate. Is non-degenerate. If the quadric is, if C is 0, then this will give you a degenerate quadric. Okay, so it will not be non-degenerate. So the C is non-zero, this constant is non-zero, then you can make sure it is 1 as well. So now in this case, if all these AIs are positive, so now again there are various cases. Yeah. So if all these AIs are positive, A11 is positive. Yeah. So for all I, let's say, so sub case. Yeah. Then what do you get? What is the picture? So for instance, all of them is 1. Then what do you get? If all of them are 1, then what do you get? A sphere, right? X1 square plus X2 square plus X3 square equals 1 is a sphere. So if they are all positive, you won't get a perfect sphere. What you get is called an ellipsoid. Yeah. So if all of them are positive, then what you get is ellipsoid. Yeah. If all of them are negative, that case is not possible, right? So because then all of them are negative, then you get that something negative is equal to something positive. So there is no solution, which is again degenerate. Yeah. So may assume A11 is always positive. One of them has to be positive. Yeah. So may assume A11 is positive. Yeah. So let's call this subcase 1, yeah, of the situation. Now subcase 2. So one subcase was all of them are positive. Now one is positive and maybe A22 and 8. So let's say we have already done the case A22 and A33 are positive. Now maybe one of them is negative. Yeah. So let's say A22 is positive and A33 is negative. So exactly one of them is negative and the other is positive. Then what you get is a one-seated hyperboloid. Yeah. So I'll not, so you can write down the equation. So maybe x1 square plus x2 square minus x3 square equals 1, and try to draw the picture of this. Yeah. So, and if you add some coefficient, it's just that the shape becomes a bit distorted, but it will look more or less this picture. So this looks like a hyperboloid, or one-sheeted hyperboloid, I think. One-sheeted, it's called one-sheeted hyperboloid. So I'll show you why it looks like this as well. I'll give you some idea on why. Yeah. So this is how it looks like. The shape looks like. So as you can see, if you look at the cross sections of X3, so let's say this is the X3 axis. Yeah. So if you fix the X3 axis, so if you fix a number for X3, then the cross sections are circles. Yeah. So even if there were coefficient, it will look like ellipse. Yeah. The cross sections will be ellipse. If you fix some number for x1 or some number, then so this is x1, and the one coming out, let's say, is x2. So these are the three axes. Okay. So so as you can see, this is how this picture will look like. Yeah. So this is what happens if one of them is positive and the other one is negative. So of course, if A33 is positive and A22 is negative, the same picture holds. It's just that the axis changes. Yeah. So the meaning case is that the other two are negative. Yeah. So A22 is negative and A33 is negative. Two of them are negative and only one is positive. Yeah. Then that is the equation x1 square minus x2 square minus x3 square equals 1. Yeah. So one example of it. Yeah. So this is also a hyperboloid, but it's a two-sheeted hyperboloid. Yeah. So this is two-sheeted hyperboloid. So it's actually disconnected, like hyperbola. So it but you sort of, it's difficult to draw the three-dimensional picture. Yeah. So it's two sort of, it looks like a parabola, but it's actually a hyperbola is what I wanted to draw. Yeah. the lower half looks better. Okay, so it's a two-sheeted hyperboloid, yeah. And again, if you look at cross sections, then it will be okay. So, for instance, yeah. So if you yeah, so here the x-axis is this one, I guess. X1 axis is this one. So if you fix an x1 value of an x1 axis large enough, then this will tell you that in absolute large or too small, yeah, very negative or very positive, then the cross sections are circles. If you fix x2 a particular number, then the cross section, so the other two axes are x2 and x3. Yeah, so it doesn't matter which one you choose. They're both negative. They both appear with negative sign. So if you fix one number there, then you will see that the cross sections are hyperbolas. Yeah. Is that okay?
Yes.
Yeah. So these are the three situations you get if so this if you assume that all the AIs are non-zero. Yeah. So this covers the case one. And then you have to deal with various other cases. Yeah. So
What about the case that AII is negative for all I?
then this has no solution. Yeah. So it's not a non-degenerate quadric. Yeah. All the AIs are negative, then the right hand side is 1, the left hand side is negative. Yeah, so there can't be any solution. Okay. Now, so now let's assume one of them. Yeah, so let's assume one of them is 0. Yeah, so. So we can always assume one. So we know that this one of the A11 AIIs must be non-zero, yeah, because we are talking about degree 2 equation. Yeah, so this diagonal matrix can't be the zero matrix. So we'll assume. So now case 2. A11 is positive. So we can assume at least one of them is non-zero, and by multiplying by -1 to the equation, we can assume A11 is positive. But maybe A22 is, and then the case A22 is, let's say, non-zero, yeah, and A33 is 0. Okay. So we are assuming that at least one of the remaining two is non-zero. Yeah, so only one of the eigenvalue is 0, and the remaining two are non-zeros. That is what we are assuming. So in this case, so A22 it could be positive or negative. Yeah, but let's just first write down this equation. So it becomes A11 x1 square plus A22 x2 square. So the linear terms for x1 and x2 can be absorbed in this one, but the linear term for x3 you can't absorb. Yeah, so let's write it here: b3 x3, and if b3 is 0, then it becomes a degenerate conic. Yeah, so we'll have to assume that b3 is a let's see if b3 is, yeah, so it need not be a degenerate. Okay, so let me just write it as, and let's call this 1. Yeah, so maybe this is also not right. So okay, so we'll do the so plus c3. Yeah, so here plus c, no, forget a c, equals 0. Yeah, so this is how we can transform it. This part is clear. Yeah, the subcase is if b3 is non-zero, then you can absorb the c in this itself. Yeah, so then this becomes A11 x1 square plus A22 x2 square plus plus B3x3 equals 0. Okay, so you can observe C if B3 is non-zero, and this is yeah, and maybe by scaling x3, we can even make sure that B3 is yeah. So I mean, we can do a scaling of x3, yeah, and make sure that this is -1, yeah. So I mean, the shape will not change, yeah. So equals x3, we can do that, yeah. So the shape of this and this with this remains same, and so in this case, B3 is.
But you no longer have that A11 is positive, right? If you do that.
Say that again.
If you scale B3 accordingly, you need not have that A11 is positive, right?
No, I mean the axis may change. Yeah, so the whether it goes positive axis or negative axis, I'll multiply by I can take the transformation x3 going to minus x3 as well. Yeah, and it will not change the shape of the thing. Yeah, it will just invert. So if you are thinking of x3 as the positive axis, if you do this transformation and look at what the image is, it just reverses it. Yeah.
Yes.
So it will not change the shape, is what I'm trying to say. Okay. So this has two cases. So it depends upon if A22 is positive, then this is like so remember, so for each value of x3 it will be a ellipse, yeah. Each positive value of x3 it will be a ellipse. So see, even if I had so let's say we put it as B3, yeah. So if each positive value of B3 x3 it will be a ellipse, each negative value it will be a empty set, yeah. So let's keep B3 as it is so that there is no confusion. So what you get is that then it is a elliptic paraboloid. Elliptic paraboloids. Yeah. So for instance, if you put 1, 1 and x B3 to be also 1, then it will look like a paraboloid. So this is how it will look like. Meaning, okay, it should pass through origin if I look at this equation. So this looks like. Yeah, so this is how it will look like. Yeah. So depending upon whether B3 is positive or negative, it will face upward or downwards. Yeah. So this is x3, x1, and x2. Okay. And if A22 is negative, then you get something else. So then this equation, it looks, I mean, yeah, so if I fix an x3, it is a hyperbola, yeah. So it's so it's not an elliptic paraboloid, but a hyperbolic paraboloid. Yeah, so hyperbolic paraboloid. Yeah, and this will be a little difficult for me to draw. So you just graph it, yeah. So so maybe an exercise. You picture it in some software. Use this one, x1 square minus x2 square equals x3. Yeah. So you try to graph it and see what shape you get. Yeah. So maybe MATLAB or something you can try to graph this. Yeah. So Yeah, so it will be sort of, yeah, so it's a complicated picture. So let me not draw it, yeah. And then what case are we in? Yeah, so if B3 is 0, then it's still a drawable picture. So B3 equals 0, subcase B3 equals 0. Yeah. So yeah, so in all this I haven't done. Okay, anyway, so then it becomes A11 x1 square plus A22 x2 square equals C. Yeah. And so for it to be, so it's either, I mean, if you forget about the x3 coordinates, then it's either a hyperbola or a parabola. Yeah, a hyperbola or an ellipse, depending upon whether A22 is positive or negative. We are assuming A11 is positive. Yeah. And if you assume it's non-degenerate, then C is non-zero, then it's either C is positive, let's say, and then it's either so this will be a cylinder. If this is non-degenerate, then this will be a cylinder over over an ellipse or a hyperbola. So it will be a cylinder over ellipse if A22 is positive, and cylinder over a hyperbola if A22 is negative. And we are assuming that C is positive. So we can assume this is 1. Yeah. Okay. So basically, you draw an ellipse and x3 goes up and down. Yeah. So it's a cylinder over that thing. And so this is straightforward. And then which case is remaining? A11 positive. So both A22 and A33 is 0. Yeah, that is the only case remaining. Right. So finally, case 3 is A11 positive, A22 equals A33 equals 0. Then the equation becomes, so maybe it's not that bad, plus B2 x2 plus B3 x3. And so maybe if both of them are B2 and B3 are 0, then it's a degenerate thing. Yeah. Plus C you'll get. But if both of them are 0, then it will be a degenerate thing. So at least one of them must be non-zero. And if one of them is non-zero, you can absorb the constant term. So you get this. Yeah. And again, if one of them is 0, then one of B2 or B3 is 0, then it's if B2 equals 0 or B3 equals 0, then if both B2 and B3 are 0, then it's anyway degenerate. So we are not worried about that. Then it is a cylinder over a parabola. Yeah. Because if B2 is 0, then this is a parabola and x2 can be anything. Yeah, no restriction on this. So, and similarly, if both of them are non-zero, then I don't know what shape you get. Then also it's a cylinder over a parabola. Yeah, so the point is you can make sure this x2, x3 axis, you can change coordinates such that this is one B2 x2 plus B3 x3 is one of the line, and on the perpendicular line there is nothing happening. Yeah. So so this by change of coordinates. So this becomes a11 x1 square plus bx2 bx2. That's it. And x3 could be anything. Yeah. Okay. So you do the change of coordinate b2 x2 plus b3 x3 is your new x2 prime, and x3 prime is something orthogonal to that. Yeah, so perpendicular to that in x2 x3 plane. Okay, and x1 you don't change anything. So that is the transformation you have to. So this is again a cylinder over a parabola. Okay, so I guess this completes the discussion about all the shapes you can get, yeah, of quadrics, non-degenerate quadrics you can get. Okay.
Yes.
Any questions or comments? So there are a bunch of degenerate quadrics, but we'll not worry about it. Yeah, that's good enough for us. Okay. So now this is more or less there's something about yeah. So there's also something about skew symmetric bilinear form. Yeah. So I don't know how much I want to discuss it. Yeah, so maybe I'll at least give you the definition. Yes. So skew symmetric bilinear form. So you know what a bilinear form. So let this be a bilinear form on a real vector space. Real vector space V. It is called skew symmetric if one of the following equivalent condition holds. If or maybe they are not equivalent always. So maybe for real vector space it is, but so let's not assume real. Yeah, on a vector space V over F over a field F. So bilinear form we are defined over any we are defined for a vector space over any field. Yeah, for symmetric if skew symmetric if V comma V, the inner product is 0 for all V in. Yeah. So it's sort of very different from, let's say, positive definite. Yeah. Meaning in positive definite, we want it to be always positive. Yeah. So this is completely doesn't make sense at all. Yeah. So in some sense, it's but anyway, this is the definition, but we'll give a other definition which works over real number, which makes more sense. Yeah. So maybe proposition that must be a bilinear form. V over F and characteristic of F. So the field has a characteristic. Yeah. So characteristic of F is not 2. Yeah? So it's 2 is invertible in that field. Then this is skew symmetric. If and only if V comma W, this pairing is same as negative of W comma V. Yeah. So symmetric means that V comma W should be same as W comma V. Here it just says that it should be exact opposite. It should be negative of this. Yeah, for all VW in. Okay. Before I get to the proposition, a consequence of this, or maybe, yeah. So what it means is that a corollary of this is let A be the matrix of the bilinear form, matrix of this with respect to some basis. Then this is skew symmetric if and only if, what can we say? If A transpose is minus A. Yeah. So this is what yeah, a consequence of. So over B matrix of this, then this is skew symmetric if and only A transpose is minus A. For if again under this hypothesis, if characteristic F is not equal. Yeah. So characteristic 2, this is not a very good property. So one has to define it. One has to look at it differently. Okay. So let's see why this proposition is true. Yeah. Proof of proposition. So this follows immediately from the proposition. So we're not going to the proof of proposition. Okay. So so maybe let's do forward direction. So both direction one has to prove. So we are assuming VV is 0 for all V in V, and we want to prove that VW in a product is minus WV. Yeah. So what the trick is that you look at V plus W in a product. So we want to do V, the pairing V comma W should be minus W comma V. Yeah. So you look at this. So one direction holds always, yeah. So this direction will hold always. The other direction requires characteristic difference. So what is this pairing? So first of all, by hypothesis, this is 0, yeah. And this is bilinear, tells you this is VW, VV, and let's write it systematically, VV plus WW plus VW plus and WV. Yeah, these are the 4 terms you will get. Yeah, and this again is 0 by hypothesis, and this is also 0 by hypothesis. So this implies VW is minus W. Yeah. So this the proof is not difficult. It's just some observation. Yeah. So this proves the forward implication. For backward implication, you look at the same thing. Yeah. So again, we want to show that if characteristic is different from 2, then this is always 0. VV is always 0. Well, VV is same as minus VV. Yeah. If you assume that VW is same as minus WV, then you take W to VV, then you get this. So this implies 2VV is 0. And since 2 is invertible, so we are not in characteristic 2, this tells you that VV is 0. Yes. Characteristic of F is not 2. Yeah, so I mean, in characteristic 2, what happens is A and minus A are the same numbers. So this doesn't lead to any contradiction. Yeah, VV is same as minus VV, it doesn't lead to any contradiction. Meaning it's possible without any problems. But if this happens in R, then you know that this number must be 0. Okay, so this is the skew symmetric matrix, and yeah. So what else I can tell you about it? So, yeah. So if it is non-degenerate, then you can. So if a symmetric matrix is non-degenerate, then yeah. So maybe. So we know that there is if this is a symmetric bilinear form, then there exists an orthogonal basis. Yeah. And if we also assume that this form is so if we choose that orthogonal basis and write down the matrix with a matrix of this bilinear form with respect to orthogonal basis, let's say B. Yeah. The matrix of this guy with respect to B. How would it look like? So it's going to be a diagonal matrix, right? Because so the matrix of this with respect to a basis is basically Aij is the evaluation of Vi with so Aij is basically, so if this is V1 to Vn, then Aij is Vi Vj. Yeah, this is how you write down the matrix of this bilinear form. So it's going to be a diagonal matrix, and what will be the diagonal entries? So it may be 1, -1, or 0. Yeah, these are meaning it is either positive, negative, or 0. And if it is positive or negative, then by scaling it, we can make sure that it's 1, -1, or 0. So by dividing by the appropriate thing, these vectors. Positive. So maybe I'll write it this way. So a bunch of ones, and then maybe a bunch of -1s, and then a bunch of zeros. Yeah. So this is how you can. So is this if we scale VIs and order them appropriately. Yeah, is that okay? Yeah, so you can always make sure that this happens. Yeah. So in fact, if it is non-degenerate, then you can assume that there is no zero. It's either ones or -1. And if it's positive definite, then we know that everything is 1. Yeah. So something similar one can say. So if so first of all, it may happen that can it happen that a bilinear form is both symmetric and skew symmetric? Is that possible?
It will be 0 then.
Yeah, say it loud.
There will be 0.
Yeah, so if it is a 0 bilinear form, so everything pairing is 0, then only it's possible. Yeah, so that's the only situation is possible. Otherwise, so if this is non-degenerate, so let's assume it's non-degenerate, skew symmetric, so skew symmetric bilinear form, then what you can say is that there exists a basis with respect to which its matrix will look like this. Then there exists a basis B. So then you can also say that the dimension of the vector space is going to be even. Yeah, as soon as you assume non-degenerate basis V1 to V2n such that the matrix of of this pairing with respect to B is, so it looks like 0, 0, and I think this is what it looks like. Yeah, so the pairing with itself should be 0. Yeah, so that's why you get zeros here, and I and yeah, so I'm not sure it's I or minus I here. So yeah, it should be minus I. It should be antisymmetric. Yeah? So A transpose should be minus A. So one of them should be minus. Yeah, so it looks like this. So you can make sure that yeah, so let me just yeah. So I think this is true. Yeah, so maybe yeah. And let me see if the proof is straightforward or. Yeah, so it will require some work. So it's maybe the proof is a bit, it may not be, so the same ideas should go through. See, V1 inner product, V1 is 0, yeah? But we are assuming, and we want to make sure that it is as orthogonal as possible. So we'll try to make it 0 with almost all vectors except 1. It's non-degenerate, so it has to be. So you'll have V1 to Vn and V1 prime to Vn prime. So you'll make sure that V1 and V1 prime, the pairing is 1. V1 and with the other vectors, it's all 0. Yeah. Similarly, V2 and V2 prime, the pairing is 1. And if you change the order, the pairing is -1. That's why this negative identity comes, and so on. Yeah, so so maybe I'll yeah, so either I'll do it as a homework or I'll think maybe we'll do an extra class. Yeah. And so this is what happens with non-degenerate Q-symmetric bilinear form. Its matrix looks like this. Yeah? So maybe this is all I want to say about skew-symmetric. So I'll think about whether to hold an extra class and discuss a little more about skew-symmetric bilinear. If it's just this one, then maybe I'll put it as an exercise with hints. Otherwise, I'll hold an extra class. But I wanted to say something about this other question about the butterfly lemma and this composition series we discussed. Yeah. So let me prove the butterfly lemma and the theorem. So remember when we did this composition series, I told you that the composition series of a group may not be unique, but the composition factors are unique. Yeah. So the length of the composition series is unique, and the factors are unique, meaning up to permutation, it determines. So to prove that, you need something called a butterfly lemma, which is this theorem. Yeah, so let me tell you what. So this follows from third isomorphism theorem for groups, but maybe after analyzing a little bit. Yeah, so let's just try to understand what this lemma says. So let G be a group. Yeah, and U and V are two subgroups of G. Capital U and capital V are two subgroups of G, and small u is a normal subgroup of U, and small v is a normal subgroup of V. Okay. So remember, in this composition series, we will have such sequences. Yeah, G1 is a group. G2 is a normal subgroup of that group, and then if you think about it. And if you have two composition series, then you'll have two such things, and you want to do something with them. Yeah, you want to compare them. So this lemma will be useful in trying to understand. So what does this lemma say? You look at the group generated by U and capital U intersection V. Yeah, so you do this cross section, U and the intersection of these two. this is of course a subgroup of U and capital U intersection capital V. Yeah, this contains it. So this is so first of all, this the product is a group because U is normal in capital U, so of course it's normal in U intersection V. Yeah, so the product is going to so the product, if you think of it as inside U, then it makes sense. Yeah, it is a group, that is. Is that okay? Yeah. So these two products are groups. So the theorem says that this smaller group is a normal subgroup of this bigger group. This similarly, this smaller group V times little u intersection capital V is a normal subgroup of V times capital U intersection capital V. Moreover, so I guess I didn't write the main statement. The composition factors are same. Yeah, so the quotients are same. And then these are the quotients are isomorphic. Quotients are isomorphic. Okay, so that is what so these are normal subgroups and the quotients are isomorphic. That's the content of this butterfly lemma. But if we draw a picture, then it will become easier. Yeah. So I mean, these two dots represent U and V. Yeah. The groups U and V. So now so this is the intersection of U and U with V, this dot, yeah. So I'll tell you the principle how we are drawing the picture, yeah. So let's call this as small u. So whatever comes below is a subgroup of this thing. So the small u comes below capital U, so it's some subgroup, yeah. And small v comes here, so it is this thing, yeah. And this dot is small u intersection small v. Okay. So and this dot is capital U intersection small v. Okay. So of course this small u intersection capital V comes under both capital U and capital V. Yeah, it comes under below capital small u and under capital V. Okay. Now this dot is basically the product of these two. Okay. So U intersection V, product V intersection U is this. So of course these two are, so the product of these two groups is a group, because the point is U is normal. Yeah. So U intersection V will be normal in let's say V. Yeah. And U, both of them. So anyway, if it is normal in one of them, then you are good. Yeah. So it will be normal in actually U intersection V. Everything lies inside U intersection V. So this is a group. So this is how we decide this vertex. What is this vertex? This is compositum of these two. Okay. So the product of these two groups. So if you think about product of these two groups, so U intersection V is contained in U. So if I want to take product of these two, I can just take product of U and U intersection V. Yeah. So this is U intersection V. So this is the product of these two. And product of these two is going to be U intersection V. Sorry, this is capital V. The first factor times V, yeah, because V contains the other factor, yeah. And this should be the product of these two. So what is the product of these two? U and U intersection V. So yeah, so So it will be U. So basically, U is contained in this thing, and U intersection V will contain. So the first factor is contained in the first factor. So first factor we leave as it is. The second factor is contained in this. Yeah. So this is just U intersection. Yeah. So this is little U. So the if I take the compositum of the product of these two, then of course the first factor we will take, and the second one is contained in this. So I can just write this way. Yeah. So I don't have to write triple product, just two products. Similarly here, if I want to do the product of these two, the first factor is contained in U intersection V. So I just have to write U intersection V times V. Yeah. Just product of these two. Is that okay? So what we will show is that so we will observe that this is a normal subgroup of this. That is not a difficult thing. What is difficult is that the quotients are isomorphic. So what we will show is that this quotient is isomorphic to this quotient, and similarly this quotient is isomorphic to this quotient. So these two are going to be isomorphic, and that is what the assertion is. Yeah. So this is the bigger group containing the smaller group as normal subgroup. This quotient is going to be isomorphic to this. This quotient here is going to be isomorphic. So these two quotients will be isomorphic. Yeah. So how do we prove that? So as I said, we'll use third isomorphism theorem. Yeah. So you take H to be this group, U intersection V. Yeah. And N to be which one am I taking? N is this one. Yeah. N is U times U intersection V. So this guy here is N. Yeah. So what does third isomorphism theorem? So what does third isomorphism theorem tells us? H times N over N is isomorphic to H mod H intersection N. Yeah. This is what third isomorphism tells us. Yeah. Right. So we just have to verify that H times N is going to be this group. If I take H to be this, N to be this, and H. So I mean, this drawing this butterfly is just for remembering. Yeah, you don't really. So if I take H to be this, N to be this group, and then show that N is a normal subgroup of Hn, and you know, H intersection N is this group. So we will want to show Hn is so Hn we have already observed. So this we have observed is U times U intersection V. U times U intersection. Yeah, because H times N is basically product of these three groups. Yeah, but this H contains the second factor. Yeah, so we can just take product of these two. Yeah, so Hn is this. So this we have done, and we want to show that. So this is okay, and we want to show that H intersection N is this guy. Yeah, if we show that H intersection. So we want to show that H mod H intersection N is isomorphic to this mod this. Yeah. So we'll have to show that H intersection N is this. Yeah. So let's just write it down. So we want to show U intersection V. H intersection N is same as U intersection V times capital U intersection small. Yeah. This is what we want to show. And then by third isomorphism theorem, we'll have this. If n happens to be a normal subgroup yeah, so of Hn. Yeah, if n is a normal subgroup of Hn, then this is okay. So that so U is a normal subgroup of U is a normal subgroup of yeah. So let's first decide that this is a normal subgroup, so that we don't have to worry about it. Yeah. So U is a normal subgroup of capital U, and V is a normal subgroup of capital V. So if I conjugate by an element of U times U intersection V, capital U intersection capital V, then I mean this will remain preserved. Yeah, but that is okay, because if so, basically a typical what does a typical element here looks like? It looks like A times B, where A is in little u and B is in intersection of capital U and small b. Yeah. So if you conjugate it by an element of little u, then it will remain, it will not change. Yeah. And similarly, if you conjugate by capital U, an element of capital U intersection capital. So this normality you can check directly. Yeah. So let's not worry about normality. Let's just try to prove that this is the two quotients are same. Yeah. So that is equivalent to saying so if I prove this, then by third isomorphism theorem we'll have this we'll have some statement. Yeah. So let's try to prove that H intersection N is precisely this. Okay. So so let's try to prove this inclusion first. Yeah. So U little u intersection V is contained in H. Yeah. Is that okay?
Yes, yes.
Yeah. So little u intersection V is contained in H, and of course the other factor is also contained in H. Yeah. And similarly, little u intersection V is of course a subgroup of little u, and hence is contained in N. Yeah. And this capital U intersection V is again a subgroup, is same as capital U intersection V here. So it's a subgroup of N. Yeah. So this product is contained in both H and N. Yeah. Because each factor is contained in H. So this part is clear. Yeah. So we only have to, so this is the trivial factor. Now let's take something in the, so let A belongs to H intersection N. Yeah. Then we want to show that A is in the right hand side. Yeah. So A is in H intersection N means A belongs to U intersection V, and A you can write it as B times C, where B is in little u and C is in capital U intersection B. Yeah, that is what we are given. And sorry, this is little u, not A. And A is in H. Yeah, so everything is in A is in U intersection V. Okay. So what do I want to show? I want to show that A belongs to the product of these two. Yeah. So okay, so yeah, so C already is in there. So C is in U intersection V. So all I have to do is show that B is in little u intersection capital V. Yeah. Then we are good. Yeah. So let's look at what B is. So B is same as AC inverse. Yeah. So this A belongs to U intersection V. So of course, yeah, so I want to show that this B is in little u intersection capital B. So why is that? Yeah, so see, B is already in little u, so that we don't have to worry about. We want to show that B is in little u intersection capital B, so that is okay. And so A is in capital B, yeah, because it's in u intersection B, since so yeah, A is in capital B, and C inverse is also in C is in capital U intersection V. So in particular, it is in small v. So it's in C inverse is also in small v, which is contained in capital V. So that tells you that B is in capital V. Yeah. So that tells you that B is in U intersection capital V. Okay. So this implies that BC is in U intersection capital V times capital U intersection B. Yeah. Because C was already in capital U intersection B. So A, which is this, is so this proves the other inclusion. So yeah, so hence this inclusion is also done. Yeah. So the two groups are same. So what we get is that so we get that this quotient. So let's just U intersection. So U intersection V mod U U intersection little v is isomorphic to U intersection V mod this guy, U intersection V, capital U intersection. Yeah. And similarly, the other one will be isomorphic to this guy. Yeah. So these two are isomorphic. Yeah. So that completes the proof of butterfly lemma. So let me stop here. Sorry for going over. And then maybe next time we will